So now we'll do the other calculus fill in the blank that from the first video. So remember, our goal is to find the electric field from a disk of charge we eventually turned into an infinite plane. To do that, we're going to start with a ring of charge. So this is an empty ring, just a circle, and it has total charge Q. One little piece of it makes an electric field directly opposite at this point over here, dE. But of course, there's a piece here that makes one the opposite direction. And on the z-axis, there's one here and one here. And everything x and y, or y and z cancels out. And the electric field is purely away from the center. It's in the x direction. So what we really need for the electric field is the integral of all the field's x components. So we need to do k dq over r squared times the cosine of the angle. So we have a triangle here. We have x and y. We have our angle. So r equals the square root of x squared plus y squared. And because we need the cosine of the angle is adjacent over hypotenuse, so x over r, or x over square root of x squared plus y squared. So now we're going to plug that in. Integral of k dq over r squared, so I can get rid of the square root. This is just x squared plus y squared, times the cosine of the angle, x over square root of x squared plus y squared. And I'm going to leave my limits of integration blank for a moment, and you'll see why in just a second. Next step, always with integrating, is to pull out all the constants. So k is Coulomb's constant, and in this problem, x is a constant. That's the distance from the center of the ring to the point of interest. Y is also a constant, except it's not y. Dang it, I did it again. This is supposed to be the radius of the ring itself. I'm so sorry. Got to change that in all these places. It was y in this, but that's equal to the radius. And for any point in the circle, it's always x and the radius of the circle to any point on it. Okay, so anyway, back to this. R is also a constant because that's the radius of the ring. So everything in here is a constant except dq. So we can pull it all out. Kx over x squared plus r squared. And just like the previous one, we have this to the first power, this to the 1/2 power. So this is over all to the 3/2 power. And then we have the integral of dq. Now remember, if we have something that we take the derivative of and then we integrate again, remember that means break it back into pieces and then add it all up. So the integral of a differential is just the original thing. So the integral of all the dq's is just the total charge big Q. So that gives our final answer of kx big Q over x squared plus r squared to the 3/2 power. So now we've got to turn this ring into a disk. Well, one way to imagine a disk, and I'm just going to draw this head on, is a disk is a whole bunch of rings all stacked together. So these rings, and of course we want an infinite, I didn't have that on the screen. Okay, a disk is a whole bunch of rings stacked together. So these rings all have different radii. The smallest one has a radius almost 0. The biggest one has a radius of the big R, the total radius of the whole disk. So if I pick out just one of them and make it a ring with a little bit of thickness, the reason I'm doing this is I can use this expression, but I'm going to change it into dq because this ring has charge dq and its radius is little r, where the whole radius is big R. So my dE now is kx dq over x squared plus little r squared to the 3/2 power. And so I need to integrate this from a radius of 0 to a radius on the outside. But my integration variable is dq. So I need to make a relationship between the charge of this piece of ring that I've highlighted in blue and the radius of that ring. So remember that this ring is essentially, it's like a rectangle, but then matched up into a circle. It's like a piece of tape or something. So we're going to define a new quantity called the surface charge density well, we defined it on the other video, but surface charge density, and it's equal to charge divided by area. So the charge dq is equal to the surface charge times whatever the area of that little ring is. That's why I'm using dA for the expression. So to get the area of a ring, this is where we imagine it as a long rectangle bent into a circle. So its length times width. Well, its width is dr. What is the little tiny width compared to r? Its length is its circumference. So 2 pi little r dr. That gives us so this expression gives us as a function of r the amount of charge. So we're going to put that together on the next page. E equals the integral of dE equals, and I'm going to copy the first dE was kx dq over x squared plus little r squared to the 3/2 power, where we need to go from 0 to big R. And then dq equals sigma 2 pi r dr. So we put these together to get integral 0 to big R, k x sigma 2 pi little r dr all over x squared plus r squared to the 3/2 power. So now we just have to integrate this. First of all, pull out all the constants. So k is Coulomb's constant, always a constant. X, remember, is the distance from what was the ring, what is now the disk, to the point of interest. Sigma is the charge density. 2 and pi are both constants of the universe. So we are left inside the integral of r and dr all over x squared plus r squared to the 3/2 power. We can't pull this x out because it's inside this expression with r. We are going to use a different substitution method this time. So, and it's honestly because this r is here, we are going to use u is equal to x squared plus r squared. So to get rid of dr, we need to have a du. So we're going to take the derivative of both sides, du. X, remember, is a constant, so its derivative is 0. Plus, the derivative of r squared is 2r times its differential. So du equals 2r dr. If we rearrange this, we're going to substitute both r and dr are up there. So r times dr equals 1/2 du. So, copying all this down, 2k x sigma pi integral from r equals 0, little r equals 0 to little r equals big R. Our numerator becomes 1/2 du, and our denominator, x squared plus r squared, is inside the parentheses. So our denominator becomes u to the 3/2 power. So before we go any further, notice we have a 2 and a 1/2. They cancel. So we have kx sigma pi. And then I don't like to do denominator integrals, so I'm going to move this to the top by changing it to a negative 3/2. And then I can use my regular rules. Kx sigma pi. I add 1 u to the negative 1/2, because negative 3/2 plus 1 is negative 1/2. Divide by the new exponent, negative 1/2. And I have to evaluate that between r equals 0 and r equals big R. So flipping this over, I'm going to do something. I'm going to pull the 2 out here because it's divided by negative 1/2. So this is 2k sigma pi. And I'm going to leave this negative with this. So there's a negative 1 on this thing, and I'm going to put it in the denominator, in the numerator, excuse me. And for the denominator, I'm going to move this back down so it's got a positive exponent. So this is u to the 1/2. R equals 0, R equals capital R. Now I need to back substitute. U was equal to x squared plus r squared. So this denominator is going to turn into x squared plus r squared to the 1/2 power. So turn the page. E equals 2k sigma pi times negative 1 divided by u to the 1/2 power, so x squared plus, little r squared, all to the 1/2 power. And we need to evaluate that between little r equals 0 and little r equals big R. 2k sigma pi. So remember, we substitute in the top limit of integration. So -1 over x squared plus capital R squared to the 1/2 power minus -1 divided by x squared plus 0 to the 1/2 power. So now I'm just going to simplify this inside. So I'm not going to write the equal sign. So this is -1 over x squared plus r squared. I'm going to change it into a square root. Equals, no, plus, dang it, equals. That's what I get for not writing it over here. So negative, subtract a negative turns into a positive. So this is 1 over x squared to the 1/2. This is just 1 over x. Did I lose an x? I did, dang it. Right down here, it was kx sigma lambda, and then when I moved the 2, there's an x on the end. There's an x, there's an x. So, sorry for the delay. I am now going to distribute that x. So I am actually going to copy down the constants. 2k sigma pi x. Distribute the x here, distribute the x here. So we get 2k sigma pi times -x over square root of x squared plus r squared plus x times 1 over x is just 1. And so this turns into 2k sigma pi times, the way I wrote it on the other video, 1 minus x over square root of x squared plus r squared. Sorry for losing the x in the middle of all of that. But that is now the equation that, with hand waving before, this is the electric field of a disk of radius capital R. And then we let R go to infinity, which made this term go away. And so the electric field of an infinite plane is just 2k sigma pi.